Hello and welcome, guys. Hope you all are doing well, and I expect that you might have subscribed up till now. If you have been following this lecture series, if you haven't then please subscribe the channel and just keep watching the videos in order to get to know more about kinetic theory of gases. So in the last class we had discussed about a ratio of specific heats and for a diatomic gas for a rigid rotator. So I'll be doing the B part today. So let's get started quickly. Okay, so yeah, we are doing ratio of specific heat, that's gamma equal to Cp by Cv, where Cp and Cv are molar specific heat at a constant pressure and molar specific heat at a constant volume. So let's start. We are doing for diatomic gases, and in diatomic gases we have done the A part in the last class. We are today doing the B part. Okay, and let me do this with a different color. Okay, so we are doing it for non-rigid rotators. In case you have directly jumped onto this video, I would suggest you that you go back and watch at least previous 2 videos in order to get to know where we have reached up till now. So let's get started. Okay, so now you have seen this thing where this is the molecule, and I'll just take this on the other side. Okay, so now if you see this molecule is having 2 atoms, one atom here and the second atom here, and there is a bond in between. But now this bond, in the previous video it was a rigid molecule, so it was not vibrating. But in this case, in today's lecture, we are going to discuss this, where this molecule is going to have a spring-like effect in between them. The atoms will be having a spring-like effect. So this molecule can vibrate like this, and this molecule can vibrate like this. So this thing was absent in the previous case when we did the rigid rotator. So let's copy and paste over here. Okay, so we are through. Okay, so now I'll just draw this. So this molecule can have a vibratory kind of motion in between. Okay, so let's count the degrees of freedom then. It's all boils down to the degrees of freedom. So it has 3 translational degrees of freedom. Degrees of freedom, and the reason is this molecule can travel in the x direction, it can travel in the y direction, and it can travel in the z direction. So it has 3 translational degrees of freedom, and it can also have 2 rotational degrees of freedom. And the reason is it can rotate around the z axis, and it can rotate around the y axis, but it won't be this rotation around the x axis won't be counted because the moment of inertia is 0. So in the previous video we had discussed I is equal to mr square. If the mass is distributed near the axis, moment of inertia goes to 0, and rotational kinetic energy is half of I omega square. So if I is 0, rotational kinetic energy is 0. So that's why we are not going to consider this rotational degree of freedom now. But in the previous video, in the previous rigid rotator stuff, we solved it by using this 3 plus 2, that is 5. In today's video we are going to see that because it is able to vibrate, I can say that it has one vibrational mode. Now, one vibrational mode brings in two half kbts, and the reason is कि when a body vibrates, it has potential as well as kinetic energy. So just keep following my previous videos, you will really understand. The story hasn't started in this particular video, it has started from some previous 2 to 3 videos. So now my equation would turn out to be like this: kinetic energy per unit molecule. So this would be equal to U upon N. That would be equal to 3 times half kBT for your translational degrees of freedom, because one degree of freedom brings in half kBT amount of energy. 2 rotational degrees of freedom will bring 2 times half kBT, and one vibrational mode will bring 2 times half kBT. Okay, and why is it one vibrational? Because there is a single spring, and because there is a single mode of vibration, it can just vibrate like this, it cannot vibrate like this, it cannot vibrate like this, or it cannot vibrate in another fashions. Had there been three molecules, something like this, then yes, it can vibrate like this and it can vibrate like this. So yes, in that case we can see that, but that would be our next video, in which we are going to discuss about the polyatomic gases. So this is what I have found out. Now let's total them. So when I total them, I'll get 3 plus 2 is 5, 3 plus 2 is 5, 5 plus 2 is 7. So I get 7 by 2 kBT. This is your energy per unit molecule. Now as we all know that N is equal to N upon Na, that is number of molecules, and this is your Avogadro's number, and this is your number of moles. Okay, so yeah, now I can just move around with this equation and I can say N is equal to small n times capital Na, just moving this on this side. So wherever there is a N, I can write as N times Na. So I'll just manipulate that. So U upon, I'll do it with a different color, maybe, yeah. So U upon N times Na equal to 7 by 2 kBT. I'll just move around with U upon N, 7 by 2 Na into kB into T. This Na just moved on this side in this particular equation, and I'll differentiate this further now. Let's differentiate. So differentiate with respect to T. So I would get du by N dt, because N is a constant, that is equal to 7 by 2 Na into kB. Oh, I just forgot to convert this into 7 by 2. Na into kB is nothing but R. This is because R is equal to Na times kB. kB is the Boltzmann's constant. Okay, so I'll just move around this. So if I differentiate this, I'll get 7 by 2, and R is a constant, so R is a constant, that's thrown outside, and I'll get dt by dt, and that value comes out to be 1. So derivative of t with respect to t is 1, so we don't write 1. So du by n dt is 7 by 2R. Now if you observe this, this is nothing but Cv, which is equal to 7 by 2R. Now by using Mayer's equation, so let's use Mayer's equation with a different color. Let's see. By Mayer's equation. Now Mayer's equation says Cp minus Cv is equal to R. This is valid for all gases. So my Cp would be equal to R plus Cv. So Cp would be equal to R plus 7 by 2R. This is filled from here, 7 by 2R. Now Cp would be equal to, now 2 ones are 2, this is cross multiplied, 2 ones are 2, and plus 7, that is 9R by 2. So this becomes 9R by 2. So I have found out Cp as well. Now the final part, wherein we are supposed to find out the ratio of specific heat, that is gamma is equal to Cp by Cv, and this Cp by Cv will come out to be 9R by 2 upon Cv was 7 by 2R. So 7 by 2R. So R and R gets cut, 2 gets cut. What remains is gamma equal to 9 by 7, and this is the specific heat for a diatomic gas. This is for a diatomic gas, which is a non-rigid rotator. So normally what happens is, okay, the gases do not stay rigid, like the atoms generally vibrate. So if you see this thing wherein this there is a kind of spring model, this thing is going to vibrate, and once it vibrates, yes, definitely your specific heat changes to 9 by 7 for today. Okay, 9 by 7 for today. Keep following the videos. In the next class we'll be doing for polyatomic gases. So just in case if you haven't subscribed it, please subscribe the channel and share it with your friends and families who are in need of these kinds of tutorials. Thank you so much. Bye.